last time we introduced some ideas around communication and synchronization between parallel processes, or work items, as we're supposed to call them in Chronos speak. Once we have those communication primitives, they can be used to enable more complex design processes. Remember, the point of design patterns in parallel programming is to get us away from the bad old days of parallel programming, where anything goes and everything communicates with everything else, and you get these horrific problems like deadlock and bottlenecks and rate conditions and the loss of the ability to debug or verify. So, the best design pattern is the map. That's the one where we just keep everything completely independent of everything else. And in many real-world tasks, especially in data science applications, you get away with this. However, other kinds of parallel programming do require some communication, some interaction. And the idea of these advanced patterns is that we are going to introduce some of that communication, but we're going to keep it very carefully controlled, very carefully restricted. By putting it in places that are known to work in the design patterns, it's going to get us away from all the problems of programming. So what we're going to see today are two slightly more advanced design patterns to what we've seen before. They are going to make some use of that communication, in particular the ability to synchronize. You know, the concept of a barrier we came across last time, waiting for all the tasks in the group to reach a certain point. At least in Chronos and OpenCL world, that's how you would implement these patterns. If you're working with other types of parallelism, if you're, for example, sitting in a very task-based parallel environment, so you're writing these containers that are going to interact, you might not require that form of communication. But we're doing the practical work in this module based on CL, and if you're working in OpenCL Chronos world, then that's the level of communication that you need. So we're going to talk about two of these patterns today. You may have heard of the first one called MapReduce, was a very famous pattern during the 2010s in particular. And we'll talk about another pattern you might not have heard of called a scan. Scan comes in a couple of different flavors called span efficient and anyone heard of MapReduce before? So anyone who's been involved in data science, and particularly the kind of 2010s flavour of big data style data science, come across MapReduce. The basic idea of MapReduce is very simple. It is a map and a reduce. We have already met these two patterns individually. Now the map is the nicest and easiest parallel pattern. It simply says do the same thing independently. And reduce is this pattern of making a tree that follows information together. You might have lots of individual data items and you can somehow combine it together. That might mean, for example, finding the sun, or finding the average, finding maps or personally by grouping data items together and then taking their results and grouping the results together. This is the basic structure of a map. For example, suppose you wish to produce products of vectors. You might be writing a three-dimensional video game and you wish to project a vector onto another vector. Maybe your character has a laser gun and you wish to find out whether that line created by the laser intersects with the target or not. The dot product operator is mathematically like this. We have two vectors, let's say they might be three-dimensional. We are going to pair them together, we're going to compute the product of the individual pairs of elements, and then we're going to sum those products together. So if you're writing a video game, maybe you have 3D vectors. If you're doing data science, maybe you have a vector with 1,000 dimensions or 1,000,000 dimensions. Data science, a dimension might be a product. You might be running an online sales platform like Amazon, which has many millions of products, and each of those products is a dimension with a vector. You might represent a customer as a vector of all the things they bought. So when you get to vectors that are that big, that's where you really need parallelism to do. So dot product is a classic example of something which can be map reduced in a single round of map reduced. Like later on we're going to see how this can go. In a single round of map reduced, we can literally assign each pair of vector elements to one of these tasks. That's the map. This would be an example of a four-dimensional map reduced. Sometimes you might be working with four-dimensional vectors, even if you're writing video games. Has anyone seen the use of a 4D vector to represent a 3D? Sometimes that is done. Sometimes it's useful to stuff in an extra dimension into 3D space that lets you do things like translations. So let's say you have a four-dimensional vector, then you're going to the task of doing these multiplications to four different GPU processing elements, for example. Each of these is going to go off and multiply two numbers together from. And when you're done with that, you then do the reduce. And the reduce just means adding them together. Reduce is doing the sum. So this bit is getting that, this bit is. If you're only working with four-dimensional vectors, like in a game, it's pretty easy to add four numbers together. If you're working with 1,000,000 numbers, then just adding those components is a large undertaking, and you really need a proper reduction in place at this point. So even if you're adding four numbers together, it's quicker to do it in parallel than in series, right? You can do it in 2 ticks this way. You're going to add these two together and these two at the same time. You're going to add the two results together. That only takes 2 cycles to do. If you were doing it in series, you use 3 cycles, 3 rounds of addition. So this is probably the simplest form of the MapReduce algorithm. MapReduce is really designed to run recursively. So you might take each of the jobs that have been mapped out by your initial task. Here's your first round of map. Finding the numbers to plug into each of those could then go off and trigger another MapReduce process. To calculate what this number is going to be, we're going to go and run another MapReduce. And to calculate what this number is going to be, this can recurse. So to calculate this one, you're going to run another MapReduce. This is usually what is meant when people talk about MapReduce. They usually mean the recursive version. So for example, let's extend our vector dot product into doing full matrix multiplication. You know how to multiply matrices together. Again, so another thing you would commonly want to do is go out and matrix is a 2D grid of numbers, and we're going to multiply 2 of these grids together to make a result. Basically, every output in the output grid is created as a dot product. So every possible row of this input gets multiplied by every possible column of this. That is a dot product. That's the thing we just calculated with 2 vectors. And that creates the result to go in a single location. So if you're doing a dot product, that's all you do. You do a single round of MapReduce. If you're doing matrix multiplication, you've got to do one of those for every point in the output grid. So a somewhat extended form of MapReduce. Do a map. We're going to take every item in this output matrix that we want to compute. We're going to map that, and each of those map tasks then becomes one of these dot products. And we just saw how to make the dot product through a round of MapReduce. So to do this, you're going to do a map. You're going to go from that map to a reduce, and you're going to have another map because that's part of your dot product. You've taken this as a component and you've basically scaled it up with an extra layer. You can map it out to every item in the grid. You can do this even more recursively. So when matrices become very large, again, say you're doing data science for Amazon, down in Cambridge, where we do it, you might have a matrix that is many millions of dimensions, both rows and columns. Every row might be a product, every column might be a customer. There are many algorithms for doing market segmentation, for example, or product recommendation that rely on manipulating these very large matrices with product consumers. So if you're asked to multiply two matrices together that have a million elements in the rows and the columns, even this level of parallelism isn't going to cut it. You're going to have to go to a much more recursive solution looking like this. Now, a property of matrix multiplication is that you can take your input matrices and you can divide them up into smaller matrices. Okay? So you see this little green window, this is a matrix in itself. This is a matrix in itself. And you can say, I'm interested in computing this item here. This is another matrix that exists as part of the overall output matrix. And the laws of matrix multiplication still function if you consider small matrices as elements of a large one. So you can say, I want to compute this element, and let's view this 3 by 3 structure as a single element. Let's view these structures as single element. I want to compute the value of this element. It's going to be this matrix times this matrix plus this matrix times this matrix. It's the normal rule of matrix multiplication, but it's being applied to elements which are themselves smaller matrices rather than just individual numbers. Okay, so to calculate this, we're going to do green times light green times light blue plus dark green times dark blue. And you can see this could now recurse. We've got a task of doing a great big matrix multiplication, take 1 million by 1 million products and customers. We can recurse that into a series of subtasks which now ask us to do smaller matrix multiplications. See? So to calculate this element, we've now decomposed that into two easier, smaller matrix multiplications. These matrices might still be pretty big, right? These might be 100,000 elements. We started with matrices that were 1 million elements. Now we've got 100,000. But then to do these tasks, we can do the same trick. We can subdivide it and subdivide it again. And that will create a whole cascade of map reductions. That's how you can do very large matrix operations. So MapReduce is famously used in web search systems. Google is a fully open source and distributed web search engine. They get to host their own instance of it on their own server, and they all talk to each other. And each node in the network specializes in finding certain words. They all communicate to look up search term, just as a commercial search engine. So MapReduce became very famous as the design pattern that powers most search engines. In particular, Yahoo's version of it was open sourced as a system called Hadoop. rose to popularity in the 2010s. They abstracted the design pattern from the rest of their web search and they open sourced their implementation of the design pattern. Later evolved into Spark, which is the in-memory version. And so what you'll see in these kinds of systems then is that same architecture, mapping and reducing. Roughly you have many nodes, computational nodes in your network. If you're a commercial search engine, they're probably all co-located in the data center. If you're an open source distributed search engine, then they're distributed. But each of those nodes is going to get given jobs from the map part. And usually that will involve specializing in particular words. So if I type in a search query with 5 words in the query, roughly each of those words can get sent to a different node in the network which specializes in that word. And that node is going to return a list of all the web pages it knows about containing that word. It's the same when we create the index. So search engines have 2 main phases. They build the index and then they use the index to answer queries. Same when you're doing the indexing. You can run Yacey at home. You'll be given certain words that your node is going to specialize in. And your node will then crawl all around the web looking for pages containing those words and making a list of those. So that's the mapping process. The reduction process then is what do you do with the results? So you might now have 5 different nodes in your search engine network, and each one has returned a great big list of results of pages responding to the 5-word search query. So your task now is to find which pages contain all those words. Yeah? You've got 5 very large lists of every website in the world. Containing a bunch of names, and the task is now to reduce them down. So there's going to be a reduce step. Usually those lists are so big, you're not going to do that on a single node, and you'll need that hierarchical structure. Pairs of nodes or groups of nodes can work together. Sometimes they're the same nodes that have been used for the map part. In other systems, you'll get dedicated nodes and specialized. So during the 2010s, this was considered very, very cool. And when Hadoop came out in particular, that there was a craze for trying to express every possible problem using the MapReduce design pattern. Hadoop gave everyone this ability to run very large MapReduce jobs very easily. So that can feel a little bit dated nowadays. That there was definitely a hype wave around these big data tools. Much of the world has moved on to Kubernetes container-based solutions with different forms of parallelism. Even if you're running on Kubernetes, you might still want to use the MapReduce design pattern, because we did see in the 2010s that you can express many interesting data science tasks just via the MapReduce pattern. So that's MapReduce. Let's talk a little bit about scans. Okay. Scan is a design pattern which extends reduce in a different way. When you do a basic reduce, you take a bunch of inputs, such as integer numbers, and you perform some associative operation on them, such as addition. And the aim of a basic reduce is to have that operation performed on everything and to reduce it down to a single result. So for example, if you're doing addition, you might have an input vector looking like this, and the aim is to add all those numbers together. And your result is going to be one number, in this case 17. It's not just for addition, any associative operator can be used. That could mean finding the mean, it could mean finding the max or the min. Many functions have the associative property. Remember, associative means if you've got f of a and F of B and C, you can swap it around. It doesn't matter what order you do the operations in. You can work on B and C first and then combine with A, or you can work on A and B first and then combine with C. So a scan is a different extension of reduce, where we keep the output, but we also return these numbers. And these numbers are the cumulative totals. So in this case, they're formed by summing up each widget at a time. If you remember the idea of an accumulator or an accumulator architecture, accumulator means you keep a running total and you return the partial results so far. So look, here we've got number 1 coming in, we've got number 1 coming out, 2 comes in and we add 2, and we've got 3. That's the running total. It's like a cash register. Every time you put in a product, you accumulate the total. Then 3 comes in, we add that to the total, it takes us to 6. 4 comes in, it takes us to 10. And we've got negative 2, which takes us down, plus 1 takes us to 9, 8 brings us up to 17. So in a scan, the objective is to return this whole series, okay, rather than just returning the number 17 as you would normally get from MP. Now, doing this in parallel is not completely straightforward. You might look at this and view it as an inherently serial kind of thing to do. Right? The whole idea of making a running total. Running is a verb, and verbs are things that happen over time, and things that happen over time are series of things. So a running total inherently suggests this idea of a sequence of calculations where you're reporting the total as you go along. So if you do implement this algorithm in series, you're going to do something like this. You're going to say, here's my vector input. I'm going to have a for loop, and this is a classical for loop, a serial for loop. The for loop is going to iterate over each object in the array, and it's going to keep a running total. In this case, we've done it in place. So we've started with the actual array here, and we're using the same array to update. But you can see this is a serial for loop. It's starting at 1 and it's going up to the size of the input array, and that means it is going to have complexity order n. Yeah? It's that classical serial loop. So it's not completely obvious how this thing can be parallelized, and it seems to have such an inherently serial character. However, algorithms have been developed. Why do we care about this? Why do we care about calculating this fairly obscure set of intermediate values? Turns out scans have loads of useful applications. In the second half of the module, Matha is going to build on these design patterns, and she's going to extend them to form particular algorithms. Stuff I've presented is quite abstract. Design patterns are an inherently abstract idea. You will see these algorithms get applied, you'll see the design patterns get applied to create many different algorithms. You can make algorithms for many of the tasks that you've seen in serial algorithms in the algorithm complexity class. So things like sorting algorithms, searching algorithms, most obviously numerical algorithms around integration. You can see this is a cumulative sum. It has the character of doing an integral. If you have a graph and you're trying to find the area under the graph, that involves cumulatively adding each chunk of the graph. So that might give you a clue that this could be very useful in numerical methods. But many classical computer science algorithms, especially around sorting and searching, can be expressed in these ways. Things to do with strings, if you want to compare strings and characters together, not just in text, that might show up in DNA analysis as well. Okay? A lot of the work in biology now is trying to line up bits of genomes and find which parts of the strings match each other. And even applications like solving recurrence relations, right? Do you remember that's how we calculate complexity equations for algorithms. So sometimes those recurrence equations get really complicated and you need an algorithm to actually find the complexity of something else. And also lots of algorithms operating on trees and operating on grass. So I know this is quite abstract at the moment. In the second half of the module, hopefully you will see how it actually shows up for real in some of those algorithms. We're going to do some scans in the workshops in CL. When we do this in practice, it's important to understand the difference between an inclusive scan and an exclusive scan. Differences in an inclusive scan, item I in the output includes item I in the input. The zeroth element, if you're using Python numbers, the zeroth element here is the number 3, and that is included in the sum. Okay, when we get to the first element, we're going to add the first element, so we've got 3 and 1 is 4. That's called an inclusive scan. An exclusive scan, we don't include the ith element in the ith output. So an exclusive scan, we always start from 0, and we take that number 3 and add it to 0, and you can see all the results shifted on by 1. So be careful with this, because different algorithms with scans might use different combinations. Okay? Those are really common case. Student assessment can be confuse an inclusive scan with an exclusive. Usually it doesn't really matter which one you use as long as you know which one it is. So I'll show you 2 different approaches to parallel scans. Remember, in parallel programming, we have these 2 different measures of complexity. We've got the work measure and we've got the span measure. Yeah? Work is the total amount of computation that gets done across all the processes together. Span is the time it would take to run if you had an infinite amount of processes available. Yeah? It's the longest path through the computation. And sometimes you want to minimize span, and other times you want to minimize work. It depends what you're doing, and it depends how many processes you have available. And so both of these algorithms are in regular use out there, depending on what you're doing and what kind of computer you're running. So the work efficient scan is called the Blalock scan. The other one's called Hillis-Steele. They're both just named after the people who invented them. This is the scan which tries to minimize the total amount of work that is done, rather than the time taken on a particular parallel machine. So the Blalock scan, it takes the idea of extending reduce algorithm very literally. When I introduced this, I explained that is the result of reduce. And the point of a scan is to create these extra numbers, giving you the cumulative sums leading up to it. So the Blalock scan does that absolutely literally. It first goes away and it calculates a completely standard reduce. Okay? So as in MapReduce, this is just dropping in the whole reduce. And you can see we've put it in here, right? This is the pattern for reduce, this is the pattern for the Blalock scan. So the Blalock scan starts by just performing a standard reduction up here. Sometimes that's called the upward step. When you have done that, and you've got the answer, you then do this extra stuff, sometimes called the down step, or down phase. And this extra stuff is going to calculate all the other values. It's going to make use of the intermediate results that the reduce pattern that produced. So the numbers coming out of here are not the cumulative sums, but they're related to them. And by performing certain extra operations, we can tweak those results to go and create the cumulative totals in the scan pattern down here. So this is a very literal interpretation of the idea of a scan. Yeah, we're going to literally reduce, and then we're going to literally do some extra work that converts the output reduce into the scan output. So in some texts, it's described through this process of up and down. You can think of starting with the data in place in vector. You can think of information flowing upwards through a network and then flowing back down again. In other books, it's written more like this, where the whole pattern just sweeps through. So they're doing the same thing. So this is the standard reduced pattern expressed as an up step. We already know how to do reduce. We start with our input vector. We're going to group it into clusters. In this case, we've picked clusters of 2. This could be much bigger. Add these 2 numbers together and store them here. We're going to add these 2 and store them here, these 2 store them here, and so on. Then we do that process again, but with a larger stride. Remember, the concept of a stride is how wide are these arrows. In this case, the stride is 1, because we're incrementing by 1 each time we position. Here the stride is 2. We're going to take this number, and we're going to add it to this number. And we're not going to touch the number sitting there. So here we've added these 2 numbers together to get this total. We've added these 2 together to get this total. And then here we've got the bigger stride. Now we're on stride 4. We add those totals together and we get the reduced output. This is showing the calculation done in place. Okay, this is the same array. It's the same physical part of the computer's memory getting updated at each step, which makes it very efficient in terms of space. You don't have to use a separate chunk of memory. So if we've done this, you can see these intermediate results are still sitting in the array. All these numbers here are still sitting in place in the array. In a normal reduce, we don't make any use of them. We make use of this total up here. If we want to turn that into a blow-up count, we are going to make use of them. We're going to look at what was created. Basically, this is a side effect of the form of the reduce algorithm. There's certain information here that has been put there. Normally it's regarded as garbage, thrown away, but we can now look at what we've actually got here and adjust it to turn it into the cumulative sums that we're interested in. So here we are in what's called the down sweep. We're going to start with the output of reduce, including all these intermediate values over here. And we're going to perform this extra algorithm. Okay? And the extra algorithm has 2 components. It's got an extra bit of reducing, that's shown by the blue lines. And it also has movement of data, shown by these dotted orange lines. In move, you simply copy the data item from one location to another location. You see this 0. This 0 has got moved over here, it's got moved over here, it's got moved over here. This total has got moved over here and moved over here. So we already know how to do reduce. This is the same kind of reduce, whatever operation we're using in pattern as a whole. So in this case it's addition, it could be averaging or finding the min or the max. Any associative. So whatever that operator is, we're going to run it going down the network. Okay? So in this case, we're going to take that intermediate total and we're going to go and add it to this intermediate total. Okay? And here we've got this one and this one, this one and this one. And roughly you can see these are doing more addition than they're feeding in to create the cumulative totals at the bottom. Meanwhile, moves are just shifting data items around at each point so that they end up in the right place for getting added in the reduce pattern. So it's not immediately obvious why this works. I wouldn't expect anyone to get it just by looking at the picture. It helps if you actually implement it, and you'll see examples of this over the workshops. But you should here get the idea that it's taking the reduce pattern literally, it's performing the reduce, and then it's doing this extra stuff. It's tweaking, it's adapting the results to turn them into this thing that you want, which is the cumulative sum pattern again. So let's try and express that a little more formally. This is using a silk-like language. So this is a language that has it's got a serial for command, but it's also got a parallel command primitive. So you find this in the language like Silk. You can express it in languages like Python. But for our purposes, it's just pseudocode to express what's actually going on. So in the upward sweep, this is the standard reduce pattern. Okay, we're starting here and we're working our way through these stages. And remember, we're doing the whole thing in place, so we only ever have to use these 8 particular memory locations. So we have the concept of a step. So this is step 1, step 2, step 3. Okay, the step is the time sequence of the algorithm. At each step, we then have the concept of a stride. And the stride is how wide are these blue arrows? Yeah? It's how far across the array are you jumping when you do your combination. So you can see here's the step. At each step we calculate the stride, and the stride is growing exponentially. Okay? It's always 2 to the power of the step. So initially the stride is 1, then it becomes 2. So once you know what step you're on and what the stride is, we're then going to go and do a map. We're going to tell each item to perform the calculation. Notice the amount of computation gets smaller at each step. So in this first step, you've got 4 items are actually doing computation. In the next step, there's only 2. In the final step, there's only 1. That means a lot of your processing elements are actually sitting around doing nothing in the later stages, right? They're all really busy at the beginning. As the calculator progresses, all these guys are just sitting around. And this is the equation telling you what to actually add together. You're taking your step, you're taking your stride, you're figuring out which 2 array items are we working with, what are we going to do with them? In this case, we're going to add them. Where are we going to store the result? We store the result in the location that the second item is already in. Yeah? There's the first item, there's the second item. We can store the result back in that second item location. So that's your basic reduce pattern. That will give you the reduction result sitting over here on the right. To turn this into a scan, we're then going to do the downward pass. So we're going to start in this state. And remember, that's got the reduction total, but it's got this other information sitting around here that normally does nothing in reduce. We make use of that information, and now we're going to work down this network, and we're going to do these 2 operations on each step. We're going to do a move. A move just means copying information from one location to another. That's the orange arrow shown here. And we're going to do reduces, shown by the blue arrows. And reduce is the same operation we did in the reduce phase, such as addition, but we're applying it in the other direction. So again, you'll see calculating the step, you're calculating the stride, the same values. It has the same overall structure. We've got a serial for loop at the top. That means working through 1 row at a time, or 1 time at a time. Within each time step, we're then going to do a parallel map. We're going to do a whole bunch of things together, as shown by this map each command. And there you see the reduction. In this case, it's addition. It could be any associative operation. And there you see the move. The move is just copying the data item from one location to another. So this is effectively pseudocode. Now let's see how that would show up in a system like OpenCL. This is where we need to make use of some of that synchronization from last time, because you can see we now have a multi-step algorithm. We've got this serial component, and within each step we're doing a parallel map component. So we're going to need some barriers to synchronize the work at each time step. Remember, when you actually run these algorithms in CL, it's not guaranteed that every member of that map is actually going to execute simultaneously. If you've got 1 million work items to do, but you've only got 10,000 processing elements available, CL is actually going to serialize some of that work. It's going to divide your requests into batches, and it's going to put a batch of 10,000 onto your GPU, and then do the next batch. So in your code, it looks like you're doing a million things together, but you're actually doing a sequence of 10,000 work items. I'm still trying to do OpenCL Chronos speak. It can be really hard sometimes. Okay? In many parts of parallel programming, we would call these things jobs, or processors, or tasks, or threads. All of those words have slightly different semantics. If you talk about putting jobs on, you're normally implying it's going to run on a big parallel compute cluster or grid, the kind of computer that's made out of many CPUs together. If you talk about putting processors on, it sounds like you're running on an operating system, because those things are called processors. If you talk about putting threads on, it sounds like you're using a particular kind of language that has threading built in. I'm trying really hard to call everything a work item instead of a job or a process or a thread in order to be completely neutral and politically correct about it. Chronos is a political organisation, and one of its purposes is to avoid getting into proprietary speech related to any particular GPU technology. If you buy a GPU from any particular manufacturer, they are quite possibly going to give you a whole new set of these terms as well. So, okay, when we convert this to CL then, we're now working in Chronos world. That means we're dealing with work items. It means we are dealing with potentially there being more work items than there are processing elements available to execute those items, and that means we're going to have to worry about synchronization as a form of communication. So here I've translated that pseudocode into actual working OpenCL. Same algorithm, you'll see here's the up sweep, it's doing this part, here's the down sweep, it's doing this part. It has the same overall structure as the pseudocode, but you can see there's OpenCL specific stuff in here. So now we're worrying about getting our global ID, we're getting the size of the work group. We're going to calculate our strides again. Notice you don't see the explicit map parallelism, because the whole thing is now written as a kernel function, and it is assumed that CL is going to launch many copies of your kernel function. Yeah? In the previous pseudocode, there was clearly a serial for loop and a map within it. Whereas in CL, you're expressing the whole thing from the point of view of one processing element, knowing that there are many other processing elements. So here's the upward sweep. That's the same equation we saw before, calculating these values, but we now have to synchronize. We've got to put a barrier there to make sure that this whole row is completed before anyone starts calculating the next row. And that's a nice basic barrier synchronization. We're not having to get into disgusting inter-process communication and all the bugs that come with it. This is a design pattern that has that little bit of communication, but it's controlled. We know where it is, we know that it works, doesn't cause us any problem. Here's the code for the downward sweep. Again, it's the pseudocode is ported again. There's the actual reduction, there's the plus operation, there's the, again, taking care to synchronize. So how does this perform? You can see it's reduction with this extra thing on the end. Okay? It turns out this, even though this is called work efficient, it turns out this is less work efficient than the serial scan. We're actually doing a lot of work multiple times as part of these calculations. That's the price you pay for being able to parallelize it. So it turns out there's roughly 3 times as many operations as just writing it as a serial scan. So the total amount of work is your only concern. Don't use any of these parallel algorithms and don't write a serial scan. That's the most work efficient scan there is. But the advantage is you get a span of order log n. It reduces log n. can see roughly we're dealing with powers of 2. Yeah, we've got 8 items. 8 is 2 to the power of 3. That means there's going to be 3 ticks needed to do this. So reduce is order log n. This extra part is also order log n. So you're at, it's like doing the reduce algorithm twice, basically. You do reduce and then you do a kind of modified version of reduce. Remember, factors like 2 and 3 don't show up in complexity numbers. Okay? We're quoting it as order n. It's actually 3 times n. We don't show constants. That's the difference between complexity theory and real life. In real life, you might very much care if it runs 3 times faster than the other algorithm. Especially if the other algorithm is being run by your competitor hedge fund, then you're both running very faster than each other. Then you really care if you're 3 times faster or not. But yeah, the important feature is it's going to get you down to order log n in terms of span. So if you have enough parallelism, okay, so Hillis-Steele is the other scan algorithm. And this doesn't take it as literally. In Blalock, you literally do the reduce and then you do more stuff. In Hillis-Steele, you try and do all this stuff together. And the idea is to make it as span efficient as possible. So we don't have this thing of doing an up phase and a down phase. And this is the structure of Hillis-Steele. You can see it's a single sweep. We form a series of our underlying operators, such as addition, but you can see in each step, some of the items are left alone. So this path is doing nothing in the first 2 steps, but then the result gets used over here in the final step. So again, you're not expected to really see how this works just by looking at a picture. You have to code it to really understand how it works, but I hope this just gives you a flavour. It's the kind of linear sort of scan. It's all done within a single pass. So again, hopefully this code will be useful to you in the workshops. You can look at it on Blackboard in the workshops. Here is pseudocode for the Hillis-Steele scan. You can see this is a much simpler pattern. Right? There's only that one pass. You don't have 2 phases like in Blalock. Here it is in Silk like pseudocode. Again, you've got steps and strides. So that's suggesting that CL implementation is going to have to synchronize to keep these steps together. You're doing the same stride calculation as powers of 2. You say, which step am I on? Which stride am I on? Here's the actual movement of data. Here's the operation, which in this case is addition, but it could be any associative operator. Let's rewrite that in OpenCL, so you can see it looks a bit more complicated now than the pseudocode, because we're dealing with all the CL-specific stuff. We've got to get our IDs, and importantly, we need this barrier sitting here. You can see there's an operation here of swapping things around, right? Swapping A's and B's around. Do we know any more efficient ways of swapping 2 data items? Might be a good place for an atomic. Yeah? Swap is one of these atomic operations which CL specifies, preferably for hardware implementation, to go very fast and to avoid any communications issue. So here's a complexity comparison of the 2 algorithms. You can see that the Hillis-Steele algorithm, it actually has the same form of complexity as Blalock, but it's faster by a factor of 2. So this is actually a place where complexity theory doesn't actually work. It's faster by a factor of 2 because it only has 1 phase instead of an up phase and down phase. You can see Hillis-Steele has more work than Blalock. So this measure does show up in the complexity theory. It has a lot more work than Blalock. So if you care about total work, maybe this is not the algorithm for you. Choosing between these algorithms is not completely straightforward. Right? Sometimes you want to minimize the total work, sometimes you want to minimize the span. And it really depends. If you're working with span theory, The span measure tells you how long it would take to run if you had an infinite number of processors available. Sometimes that's a reasonable assumption. If you're working with relatively small vectors and you're running on a GPU with 10,000 processing elements, you might assume you've got basically unlimited parallelism available. In other times, if you're doing things like data science, you've got matrices with many billions of items, then you care much more about the total work that is done. Because even if you express your algorithm in parallel, it's still going to end up getting serialized and put on your processing elements in batches. So in most cases, you do need to think. You need to think about what hardware are you running on, what are you actually trying to do, and which is the right algorithm for you. Yeah? Two computing span algorithms. Wouldn't that make a nice exam question? You know, compare and contrast two computing span algorithms. So, you know, what situations would you use Hill, Steele versus So Scanner's just got very interesting a few months ago. You might have heard of this little thing called the transformer architecture, called attention is all you need. That is the foundation for large language models and all the other trendy AI systems we're using. And until last October, it was assumed that all that benefit has come from this fancy new algorithm called attention. From the transformer. Like the transformer is a new kind of neural network. It encodes position as part of its vector representation, and it uses a equal value system instead of the normal rules of sigmoid neural net activation function. And since 2017, the world has been obsessed with these things. They're powering ChatGPT and Llama and all this stuff, and it has been assumed that the genius part of it was creating this transformer algorithm. The point of a transformer is you can train the things in parallel. The conventional way to train language models was a recurrent neural network, which computes one word at a time in sequence through inherently sequential algorithm. And the point of the transformer is that it has a fast parallelizable training algorithm. Last October, someone noticed you can actually take the recurrent neural network equations, which look like this, and you can express them in terms of the scan. They've implemented it using the Blalock scan, and they found it enables you to go back to original 1990s style recurrent neural networks and build models that perform as well as ChatGPT type systems using a 1990s RNN rather than a trendy 2020s transformer. So this suggests that actually all the gains that have been made in this round of AI are entirely due to architecture and parallelism and GPU power and buying stuff from NVIDIA rather than advances in this fancy transformer algorithm. So this has recently been productionized into a specific large language model called Member. So if you're running LLMs at home, try out Member 7 billion parameters. This is a transformer-free LLM, and it's running on old-fashioned RNNs using the Blalock scan.